Okay, so welcome to this week's Origins Colloquium. It's a pleasure to have Subbu Mohanty visiting us from Imperial College London. So Subbu graduated from UC Berkeley in 2002, so we overlapped substantially there, which was very nice. He was then he worked there with Gibor Basri and Frank Xu. I mean, the thesis was to do with brown dwarfs at the time, right? That recently been discovered, just chatting about. Then he was a postdoc at Harvard, first on the SIM mission, and then later a Spitzer Fellow at Harvard, further developing ideas on formation of brown dwarfs and towards protoplanetary disks and planet formation. And then in 2008, he joined the faculty at Imperial. And so we've been working together a little bit over the years now on various aspects. And yeah, he has tell me about 5 PhD students there, so quite a big group working on these topics. So if you'd like to chat with him more, well, we'll have a discussion, of course, after this. But you're still around for a few hours.
Yes.
Right? Very good then. So please go ahead, Subbu.
Thank you very much. I think I'm going to stand up and
Yes.
take off my coat. I don't know if I'm also on here as a face or
They can
doesn't matter.
It's this camera here. They can see you. So you can
Really?
compare into that little thing there. It's a fisheye lens.
Right. So I don't know if
sorry to interrupt, but can you share the other screen because we see the presenter mode online and not the full screen version? That would be perfect. That would be much nicer.
Yeah.
Thank you, Subbu.
Yeah. You'll have to tell me how to do this. I'm not sure. Why? I see swap displays.
Yeah.
Is that better?
We get that.
Oh, yes, that's much better. Thank you very much.
On here, but not here. So how do we do that?
Use slideshow, maybe?
Yeah, but like when you start sharing screen in Zoom, can you then
Share the
choose
desktop,
which
basically.
Oh yeah, if you stop sharing on Zoom
Yeah.
and then reshare, it should give you the option to share only the presentation, not the presenter view.
Hang on, so just a moment, sorry.
Take that off the screen.
And show. Right.
Yeah, if you start the slideshow, then
Back on Zoom. Okay, there we go. Right, so I start slideshow on here. Is that what you mean?
yeah,
Okay,
and then
play from
see
start.
okay, swap this.
Where is it?
If you drag your cursor over off to the right hand side of the screen, then
Oh, I see.
swap that,
Swap that.
and then when you share on Zoom, only share
Oh,
that screen.
so now I've got to go and share on Zoom. Where's it gone now? Where's Zoom gone? See?
Bring up the taskbar.
I would if I could.
In Zoom, I would share that desktop and just put the thing there. And
Yeah, maybe I'll just do that.
try and find Zoom.
Escape, come on. Fucked off. Gosh. Okay, back where we started. No, this is just taking me through my show. So people on the other side now see
Nothing. You're not sharing.
because I'm not sharing at all. End show.
Can you minimize this so that you can see what's behind?
Yeah, it's just that I don't see my cursor here at all.
It's on the
Yeah,
reachable left.
End show. Right. Zoom is here.
Yeah.
So here, if I do a share screen
Share the desktop.
and share the
Desktop one.
this one here. Okay.
Okay.
Okay, I see. And then do the I see. Do slideshow, play from start.
Yeah.
And everyone can see
We're
the
all
same
good.
thing. Very good. Sorry,
Yes.
thank you.
This is perfect. Thank you.
5 minutes left
Okay.
now, Subu.
Right, exactly. 5 minutes left. So I want to talk to you today about how to form super Earths and sub-Neptunes. And this is stuff in fact, it was Jonathan who inspired me to begin to work on this in 2014. Large number of people at Imperial and other places, former PhD students and new ones who are also working on this. So I'd like to introduce these objects to you a little bit. Some of you already know about them. And then I'd like to introduce you to how we think, or the reasons we think they form in a specific location in the accretion disk. And after that, actually speak a little bit about how we think they might form in that location, okay? So super Earths and sub-Neptune, so these are all the known planets as of 2 years ago. Most of these, or at least all the objects in here, you can probably see my cursor there, yeah?
There it is.
Are all essentially discovered by the Kepler Space Mission. And so I'm interested in all of these planets here, okay? And in particular, the super Earths are these guys here, which range from about half an Earth radius to about 2 Earth radii, so Earths or super Earths. And then the other guys are the sub-Neptunes, which range from around 2 to around 3.5, 4 Earth radii. Okay, so these are the two objects we want to look at. And the first thing I want to draw your attention to is in our own solar system, look at the orbit of Mercury, right? Which is shown on there at around 0.4 AU. And the majority of these things lie inside the orbit of Mercury, right? So in other words, first thing we know about them, and also to point out that these things are incredibly common. Okay, we already know that at least 30% of all stars, sun-like as well as M dwarfs, have these planets, and it may be even more around M dwarfs. We think the statistics might be as high as 80%, but at least 30% of all stars. So overall, these guys at least represent a really important outcome of planet formation, and perhaps the most important outcome of planet formation. And also, we don't have these planets in the solar system, right? So we need to understand how these things form, and also the reason we don't have them in the solar system. Okay, so in terms of the properties, first of all, they are small, as I said. They have a radius of about an Earth to around 4 Earth radii. They're also close into the central star, essentially less than 100-day periods. The other interesting thing about them is they have a bimodal distribution of radii. So if you look at that, you'll find, so these are the number of planets per star at orbital periods of less than 100 days. And so the histogram of those in terms of the planet size, the radius of the planet in Earth radii. And you see clearly that it's got 2 sharp peaks, or 2 obvious peaks, and in between them an equally obvious gap. Okay, so the first one is a peak around 1.3 Earth radii, the other one around 2.4 Earth radii, and in between them is a gap around 1.8 Earth radii. Okay, and this is observational, and it's now established beyond all doubt. Okay, so we have that, and also the smaller peak appears to be observationally, these appear to be planets which are essentially solid rock iron composition things. Okay, and they hardly have any obvious atmosphere. Okay, they may have an atmosphere like the Earth has an atmosphere, sort of a thin atmosphere, but it's certainly almost all of the planet's mass is its rocky or iron rock core. The other guys, observationally, are planets comprising a solid core and an envelope around them of gas. Essentially hydrogen, helium, if you like, and we can have discussion about that later on. And in those cases, the envelopes are a few percent of the planet's mass in mass. Okay, so these are the 2 peaks. These are just observational facts about this, right? Third observational fact: they often are found in tightly packed planet systems. Okay, and here's right. So here's the distribution of some fraction of these things. I think these are all the systems that are known right now, which have super Earth and sub-Neptune planets and have more than 4 planets in the system. Okay. I've also highlighted in their Sol, our own solar system, right? And you can see that our own solar system looks very, very unlike the other ones, right? So it's got these small planets out beyond around 0.4 AU, right? And these are all small planets here. All the other ones, as we have already seen, our solar system does not have these super Earths and sub-Neptunes, and so that is obvious in this diagram. The other thing, though, the important thing about this diagram, as far as I'm concerned, it's not a point that the authors made, but a point I would like to make, is that you can see in all these systems, super Earths and sub-Neptunes are mixed up together, right? You find in the same system, you find some super Earths, you find some sub-Neptunes, right? And the size of these dots is a planet's radius over here, right? The smallest one is an R, 3R, etc. Right? So in the same system, you find super Earths and sub-Neptunes mixed. And that's going to be a really important point because of this. Okay, so I'm going to introduce an idea first, and I'm going to say the bimodal distribution of radii we have seen, and the fact that these are in tightly packed multi-planet systems together imply that super Earths and sub-Neptunes are born together in accretion disks at the time that you have a lot of gas around. Okay, so these things are born together early in the lifetime of the disk when it has a lot of gas. Why do I say that, right? How do I infer this, right? And I think this is an extremely important point that is not sufficiently actually made. Okay, so imagine you do have a planet in a gas-rich disk. Okay, so I'm going to go back to this and I'm going to take these here, right? So imagine you have a planet that has formed a gas-rich disk and it accretes an atmosphere. Okay, so in this case, I show you two of these planets and the star. Okay, so you have a small planet. It's either small or it's close in, and it has an atmosphere around it. And you have another one which is somewhat larger and all further out, right? Because these planets are sitting so close to the central star, because of the heat of the central star, the incoming irradiation of the central star, they start losing their atmospheres. And if you do the calculation, you find that the inner one, or the smaller one, is going to lose all its atmosphere, and the other one is going to hang on to some fraction of its atmosphere, about a few percent or so. Okay, and it has some involved physics in there, which we can talk about later, right? But this automatically, it gives you super Earths and sub-Neptunes. Okay. Now, but it also makes a prediction, a quantitative prediction about which planets should be super Earths and which planets should be sub-Neptunes, right? Depending on mass of the core as well as distance, orbital distance from the star. Okay. When you now, so there's instead all of this is because of XUV, X-ray, and UV irradiation from the central star and some other stuff I don't want to talk about right now, but essentially evaporation by irradiation from the central star. When you go and look at this kind of arrangement, the observed architecture of these things, what you find is that the arrangement of these things, right, small things closer in, large things further out, etc., is exactly as you would expect if you had photoevaporation, right? And therefore, if you think that you form these sub-Neptunes which have some gas around them at an early time, and the super Earths which seem to be essentially naked cores at a later time, and then they have dynamics, etc., and they put themselves into this arrangement, there is no way statistically that they would arrange themselves in a way that agrees with predictions of photoevaporation, right? So it's a self-consistency agreement. Argument, right? And this, to me, I think is the clearest evidence that super Earths and sub-Neptunes have to form at the same time, and they have to form when the disk has a lot of gas in it. Otherwise, you can't accrete a lot of gas, and therefore the formation is not like the Earth's. The Earth formed much later in the disk lifetime when it had lost almost all of its gas. These things are not forming like that; they're forming early in the lifetime. The other thing that photoevaporation also implies is that the composition of the cores is the same, right? That's the argument that we just made, right? And finally, the composition is Earth-like. In other words, it's a rock iron core. We already know that by looking at the super Earths. We know their composition because we know overall there's hardly any atmosphere. So we have, observationally, we have their size or their radius. Observationally, we also have the mass. You put the two together and you have a rock iron density, right? And the sub-Neptunes as well, we have some observations, but also if you invoke photoevaporation, then the amount of photoevaporation you have depends on the gravitational potential that the gas has to escape out. Therefore, it depends on the composition of the core, right? Ice doesn't have the same density as rock iron, right? And therefore, if you do those calculations out, then what you find is, you don't care about this, but you find that the core composition you end up, or the observations imply that you have to have a core composition that is iron rich. Okay, it's not ice rich. Okay, so rock iron compositions. Okay, so where do we go from here? Right. So we have these facts, and now we've established that these guys are essentially Earth composition in their cores, also form when you have a lot of gas around in the disk. So how do we form these things? How am I doing on time? How much time has elapsed?
At least 15 minutes left. Maybe 20 maximum.
20 minutes, fine, I'll be fine with that. Right. So, first thing I should say is that if you think of an accretion disk around a star, as you go further away from the star, it gets cooler and cooler and cooler. At some point, you have the ice line. I haven't said all this here because this was, anyway, it's an expert's talk. I understand that everybody isn't an expert. So as you go further and further away from the central star, the disk becomes cooler and cooler. At some point, you have an ice line. The ice line is where H2O essentially condenses out into its solid form. Okay, so if you have to have these things which are mainly essentially rock iron composition and not icy composition, they have to form interior to the ice line. Okay, otherwise you'd end up with icy cores. Right? So, but when you try to form these things in the inner parts of the disks, which is the location we find them in today, and we would also like to form them there, is the overall idea, right? So the fundamental problem is that the inner parts of the disk don't have enough solid material. If you invoke the sort of standard minimum mass solid nebula model that is invoked to form the solar system. That by itself is not surprising because the solar system doesn't have such planets, okay? So the mass distribution that you infer by looking at the solar system doesn't have enough material, okay? So, well, that's not a tragedy. You can just increase the amount of material in the solar system, increase the amount of gas and dust in the inner disk and form these things. But that leads to a problem, okay? So essentially, if you invoke a scaled up MMFN, right, increase the amount of inner material, that leads to the problem that scaling up the MMSN to get enough amount of solids in the inner disk to form these super Earths and sub-Neptunes, while keeping the dust to gas ratio the same as you find in normal accretion disks, gives you way too much gas. The interior becomes gravitationally unstable. Okay. The other bit is that if you also have too much gas, instead of forming super Earths and sub-Neptunes, you form giants, gas giants like Jupiter. Okay, neither of those two things are true. Okay, hot Jupiters make up only a tiny, tiny fraction of all the planets we know, less than 2%. Okay, these guys, on the other hand, make up about 80% of all the planets we know in the inner disk. Okay, so you can't do that. So you can't simply scale up the MMS. How about if we invoke the other thing, which is migration of planets, right? For hot Jupiters, that's the idea that is invoked. You form these planets out somewhere where you do have a lot of material in the disk, right? Outside, beyond the snow line, and then you form them out there, you migrate them inwards. There you can already see the problem. Let's not think about the apparent problem. That's for experts. Real problem is that if you form these guys beyond the snow line, you'd get a significantly icy composition. Okay, so this is sort of a simple bottom line. That's not happening. Okay, we know these things are rock iron in composition. Okay, so that seems off. So now what we do is we invoke a hybrid model. Okay, we say, okay, essentially, in order to form these rocky objects, we need an enhancement of the solids in the inner disk. We don't need all that much gas, right? So if you have all these solids in the outer disk, why don't you get them inwards into the inner disk? We know that this kind of flow already happens because the dust and the gas have dynamical interactions. And basically the dust, it faces a headwind from the gas and it is robbed of angular momentum and it flows inwards. And we see evidence of that already in Helm observations. Okay, so you have all the solid materials in the outer disk, migrate them inwards, and assemble them into a planet in the inner disk. Okay, so migration of solids and assembly in the inner disk. So it's a combination of these two things, right? You can do this in two ways. You can do a migration of solids and a full assembly in the inner disk. And by full assembly, I mean you grow all the way from grains of dust up to planets. Okay, an example of that is the inside-out formation stuff, which I'm sure Jonathan has also spoken to you about a number of times. Basically, you get solids coming in from the outer disk, and then as you get into the hot inner parts, because of the way the viscosity behaves, you have a pressure pump in the gas on the outer edge of the hot inner disk, which is able to trap some of these solid particles, and they continue there and become essentially larger and larger. You might get the streaming instability, at which point these things sort of gravitationally collapse into embryos. Eventually, you form a planet there. And you may, in fact, have a sequence of planets that forms here. But the point here is that you grow all the way from grains up to planets. Okay.
Pebbles, the pebbles have to drift in.
Yes. Sure. But these are essentially centimeter, millimeter sized particles, okay? And then you do the whole thing up from there. The other thing is migration of solids plus partial assembly in the inner disk, or you can also call the same thing, the same acronym, migration of solids for pebble accretion in inner disk. What I mean by that is this, right? Is that you form planetary embryos close to the snow line over here. Okay, and these planetary embryos are about a tenth of an Earth mass or so. When they form around the snow line, there'll be about 30, 40, 50% ice, and that's fine. And around them, you've got all these icy pebbles and so on. These things will continue to flow inwards. As the embryo flows in, and then it arrives in the inner disk, it is accompanied by all the icy pebbles that also flow. Notice now that the icy pebbles lose their ice mantles as they enter the inner disk because it's too hot, the ice sublimates, it's inward of the snow line, okay? So now you've got this icy embryo. The embryo is large, okay? It's not going to lose its internal ice content. It may continue to be 50% ice, right? But the embryo is only a tenth of an Earth mass. If it grows by accreting these pebbles that have accompanied it inside in the inner regions through this pebble accretion business, then it still needs to accrete 90% of its mass from the pebbles which have lost icy mantles. Okay, so pebbles are all rocky, right? So 90% of the accreted mass is all rock, no ice. So the end result is basically a rocky super Earth or sub-Neptune. Okay, so that's sort of the partial accretion idea. Okay, now, so 10 minutes? Yeah, good. So this is all, ideas and hand waving, but how do we actually see if any of this is true? Well, you really have to look at the physics of the inner disk, which is really, really complicated stuff. You've got gas, you've got dust, it's hot, you've got non-ideal magnetohydrodynamics, etc. So we decided that the first thing we want to do is to look at the structure in the inner disk of the inner disk gas. Okay, and we're going to simplify the problem to start with, and we're going to look at this when the accretion rate is a constant. In other words, the disk is steady state. Okay, so that's an approximation. It's not true. The inner disk is not actually in steady state, but we're going to start with it. So we included a lot of physics in here: non-ideal MHD, disk heating by viscous accretion, stellar irradiation, radiation and convection, dust opacities, all kinds of effects in ionization from X-rays, cosmic rays, radionuclides, a chemical network that accounts for alkali species, which are thermally ionized, non-alkali species, which are not thermionic ionic emission, charged dust grains, absorption of particles onto charge, etc., etc. Okay, so all the important physics, and some kind of grain size distribution as well. So I'm not going to say. And so the important thing here is first of all the viscosity in the gas, right? So we sort of infer the viscosity in the gas self-consistently, and the viscosity is because of something called the MRI, the magnetorotational instability. So you have got to do the non-ideal MHD stuff and the ionization, convert that into an alpha. The point here is that here's sort of the distribution of alpha in the top plot. And you can see that it is high in the inner parts of the disk here and just essentially dies out here. And that's because alkali ionization just exponentially falls off as the temperature falls off, right? Okay, excellent. Then we have all kinds of graphs here. The important graph here is this one. Where's it gone? This one here, which is the pressure in the midplane as a function of radius, right? And as you can see, we find that the pressure indeed has maximum in the midplane, okay? And this is exactly the kind of pressure maximum that Jonathan would like to invoke to be able to trap his grains, okay? So we do find that. And then we show this pressure maximum as a function of, accretion parameters, dust to gas, M star, etc. I'm not going to go into that. This is just to show that we have done these calculations. This doesn't matter. And then we also looked, okay, so now we have solved for the structure of the gas in this disk. Now we want to look at the dynamics of dust. Okay, and so we sort of look at this in a simplified fashion by looking at the dynamics of the dust embedded inside this steady state gas disk. Okay, so we leave the underlying steady state gas disk solution fixed, and then we say, I'm going to throw in there some dust and see how it behaves. Okay, and then we have, all kinds of physics in there, unimportant to talk about at the moment. It includes the fragmentation of the grains, coagulation of the grains, inward sort of drift because of advection and because of diffusion, and so on and so forth. And so we solve the dust advection diffusion equation including coagulation and fragmentation. And we arrive at this, okay? So we say, if the grains are coming inwards from the outer disk at some accretion rate compared to the gas, right? So the important thing is the accretion rate of the grains compared to that of the gas. So either it's accreting inwards at the same accretion rate or at 10 to the minus 1 of that or 10 to the minus 2 of that. We start out, by the way, with an initial dust to gas ratio of 10 to the minus 2. So saying that the accretion rate in the grains is 10 to the minus 2 of that in the dust is just saying it's coming in at the same sort of fixed dust to gas ratio. Anyway, the point is that after around 0.2 billion years or so, it seems to achieve a sort of steady state in the inner disk. And that by itself is very interesting because you see
that depends on your outer boundary, maybe.
That depends on the outer boundary. But overall, I mean, I'm not saying any of this is true, right? I'm just pointing out some of the things that can happen, right? First thing that you see that the amount of dust that is trapped in the pressure maximum is not that high, right? You have a small little bump at the pressure maximum. It's not a large bump. The other is that there's a large amount of dust in the inner parts inwards of the pressure maximum, okay, in the inner disk here, right? I mean, the dust to gas ratio can be all the way up to unity, right? The same amount of dust and gas. So it really starts building up there. And all I thought I'd show you is the physics of that. And the idea is that even as the dust starts to flow in, the viscosity, the turbulence in the gas is high because the viscosity is high. But especially as you approach the pressure maximum and inwards, the turbulence is very, very large, okay? Because the magnetorotational instability drives turbulence, which drives the viscosity. It is basically turbulent viscosity, right? So inwards in the inner parts of the disk, it's a high turbulence. And so any grains, so the grains are already starting to become small enough that they're not efficiently being trapped in the pressure maximum. And as they come inside, they become very, very small indeed because of all this turbulent fragmentation, okay? And as they become very small, and these things are tiny, right? These things are particle size of 10 to the minus 3 centimeters, right? So as they become really, really tiny, then they become entrained in the gas. Okay, so they basically start acting like gas particles. So they don't drift inwards into the star, but they hang out in the inner disk as really tiny particles, right? So in this scenario, it's quite hard to imagine how these very tiny particles would then become larger dust particles and grains and pebbles that you need to construct planets. Okay,
But the gas is flowing to the star.
yes, yes. So these things are flowing in on a viscous type scale, as opposed to if you had centimeter-sized particles, they'd start flowing in on 100-year time scales. Right. So it's not a drift type scale. Okay. This is, I'm not going to go into that. I can come back to that later. But the thing I would like you to observe in this, though, the important thing here is that the final distribution of dust we had is not the homogeneous distribution of dust that is assumed in our underlying steady state disk, right? Is that all this stuff flows inwards, accumulates in the inner disk, etc., etc. It starts out as large particles, becomes very small particles. All of this is saying that if you assume a steady state and you do things to it and you find out in the end it doesn't look like your initial assumption, then your steady state assumption is meaningless, right? So what that really means is that to understand any of this, we really need to have time-dependent 2D dust plus gas dynamics. Okay, so that's the conclusion. So all of this, it gives us sort of hints about things which might be going on for planet formation, regions which might be more sort of effective at forming planets, impediments to planet formation, but really we don't have any answers until we actually do the whole thing. So that's what we are starting on now. So I'll just explain this in a second or just lead you through it. So these are time-dependent 2D gas and dust dynamic calculations using something called a QDisk. QDisk is a new GPU-based code optimized for gas and dust evolution in protoplanetary disks. This has been developed in-house at Imperial. Okay, and it includes all the earlier physics I had shown you, all of the stuff in blue, but the new stuff in it is that, well, the test point is an interesting point. It's not all that, well, I mean, I'll say. So earlier on, when we were solving our chemical networks and stuff, you really have to do the grain size distribution correctly. Okay, and in particular, you have to do the grain charge distribution very, very well. Earlier, people had sort of ignored this because people were thinking in terms of the viscosity of the gas, which really cares about the ionization state of the gas, okay? The ionization state of the dust particles was not really considered to be that important, apart from the fact that it soaks up charges from the gas, okay? But of course, how much the dust particles are able to soak up charges, etc., depends on their size distribution. But more importantly for us, the size distribution of the dust particles is very important, right? Because these are the things which need to collide and coagulate to become larger and larger, right? And if the dust is charged, as you can imagine, it becomes harder to stick together. It becomes harder to fragment if you are large, but it also becomes harder to coagulate if you're small. Okay, so now we actually solve for that self-consistently for arbitrary size distributions. Okay, so that's fine. But the important part about this particular code is that it has the two-dimensional dynamics of the dust. So we solve the grain advection diffusion equation and the Smoluchowski equations for coagulation fragmentation in 2D. And so that includes diffusion, drift, as well as settling, which is really, really important. Okay. And also we include the gas dynamics. In particular, this is also very important, the back reaction of the dust on the gas, right? So I said earlier that the grains drift inwards because they face a headwind from the gas, which robs them of angular momentum, right? So, okay, but that angular momentum and momentum overall has to end up in the gas, which then also changes its own movements, right? And that becomes really important when the dust to gas ratio is very high. As long as the dust particles are only a trace species, it doesn't matter, right? But as soon as the dust particles become comparable to the amount of gas there, it becomes really important. And of course, that is sort of the regime that we would like to be in if we want to form planets, right? So that's included in there now as well, so we can really follow these things. This is my last slide. I thought I'd just show an example and then leave it. So I'm on time-ish, I think, okay? This is interesting just to show the kinds of effects you can have, right? So we start out, this is this sort of, I'm showing you here the evolution of grain sizes because of the physics in the gas and the dust, okay? At a particular location in the disk. So this is at 1 AU in the disk at the in plane of the disk, right? And I think the assumed temperature is like 1,000 Kelvin or something. Just sort of an example of the things you might expect, right? In this location, we initially start out with an MRN distribution of grains. Okay, so it's sort of an ISN-like distribution of grains. It's a power law distribution with an exponent of the power law of minus 3.5. So that's shown here in green here, because that's, if I can find my cursor again, right? So the green stuff is the initial distribution, and it has then an exponential cutoff in that at some large sort of grain size. Okay. And then we say, okay, at this location, we will have either a disk, which has a viscosity parameter alpha of 10 to the minus 3, or a viscosity parameter of 10 to the minus 2. So the larger alpha is, the more amount of viscosity you have, but also the more amount of turbulence you have. Okay, so basically the alpha here stands in for the amount of turbulence in the disk. And so the alpha of 10 to the minus 3 solutions are shown in orange, okay? And the solid line in orange is the grain size distribution in the midplane of the disk, and then the dashed line is up at a scale height of the disk, okay? And it's really interesting, right? So the first thing you see is that the orange curves, alpha of 10 to the minus 3, at the large end, okay? So along the x-axis over to the right, right, it gets a lot of large grains, okay, because coagulation is happening and these grains are getting together to form larger grains. But it also has more amount of fragmentation. So if you look at the zoom in here, right, you can see that the orange line at the small end of things is also above the initial distribution, right? So you get a lot of coagulation and large grain formation at the large end. You also get a lot of fragmentation, etc., happening at the smallest end, to be expected. But you also find that the size at the midplane is larger than the size at a scale height. And that's because you're also seeing the effect of settling, right? As grains become larger, they settle out in midplane. And so you see all of these effects here. But if you look at the blue lines here, which is alpha of 10 to the minus 2, so a higher alpha and so an increased amount of turbulence, what you find is what you expect, but it's nice to see it in this kind of simulation, right? First of all, you see that you get not that many large grains compared to the initial distribution. Why? Because the turbulence is higher, and therefore when you have collide, it's much more likely you will fragment rather than coagulate to large things. Similarly, at the small end, you find that it is much higher than the initial amount in small grains because fragmentation is more efficient, and certainly higher also than the alpha equal to 10 to the minus 3 case because it's more turbulent. And finally, you also find that the distributions are almost the same at the midplane as a scale height. Why? Because you get more amount of turbulence, which is able to loft things higher again, right? So it mixes up the scale height. Right. So these are the kinds of effects which are being accounted for. And on top of that, also the diffusion, advection, the viscous diffusion as well of the gas going inwards, right? So you put all of these things together and hopefully be able to show you some results in 6 months. Okay, so stay tuned. I shall stop here.
Great, thank you very much. It's not time for questions and discussion, and so raise your hand in Zoom or here if you have questions for Subbu. I have many, but I'll hold off for a second. So yes, please, Oliver, go ahead.
Yeah, hi, Subbu. Oliver Herbert here from University of Vienna. I was actually wondering about one thing. You showed earlier in your sketches that the constant temperature across the snow lines, like in this case, for example. But if you look into more detailed models, you will have like quite a different temperature in the mid-plane, which is significantly colder because it's shielded. Is that also included in your models, or
Yeah,
because that would automatically increase the number of condensates in
absolutely.
the closer parts to the star and can somehow help with this?
Absolutely, yeah. So these sketches, I have to admit, I only constructed this at 9 a.m. today. So this does not take vertical temperature structure into advance, which is beyond me in some sense in these things. Absolutely. We do have, it's not isothermal vertically at all in our things, and we do take a vertical temperature structure, and therefore we do expect the chemistry, if you like, and the thermal physics, etc., to change as a function of height. Absolutely.
Let me ask a follow-up question on this model in general. I mean,
Yeah.
how good at trapping? I mean, why planets should form at the ice line? Can you remind us? Is there a pressure trap there?
Yes.
Or it's not a very strong one, I would imagine.
Well, I mean, it's a snowline trap, right? So it's just that outside it, you get your ice mantles. Inside it, you don't get ice mantles. You have a jump, therefore, in sigma, and therefore you have a jump in alpha.
Maybe it's not really like pressure, it's more like a traffic jam more than
Yes. It's not a trap, it's a jam, if you like.
But there is a local pressure maximum in the gas.
Yes.
Due to water, just the water vapor coming up.
That would be. You're the expert in this stuff, aren't you?
So like it depends on the models. Like you can have like pressure, like a pressure bump, but you don't necessarily have like a pressure maximum in the sense that you don't necessarily have an inversion of gradient for the pressure. So that's like that would be the difference between like a pressure trap and a traffic jam. In one case, you have like a change in pressure, but you don't have like the inversion. If you look at the difference between the azimuthal velocity normalized by like the Keplerian velocity, then you may not have a real inversion in pressure. So you may not have a real pressure max, but you still have like a traffic jam because the particles like they have different speed.
So you mean in other words, what you mean is that if you look at this pressure plot, you'd have a change in the gradient.
Exactly. Yeah.
Okay, but it doesn't.
Right. Well, my sort of follow-up to that was really how predictive are the models of forming embryos here? Like,
Well, so
are they just inserted? Or?
Yeah, so I have to say that that all this stuff I show around the snow line here is not stuff that we will do. Okay, we are going to concentrate on the inner disk part of it. So insofar as embryos coming in from the outer parts of the disk, we are going to use parametrized versions of that. The models of it are reasonably sophisticated. Most of these are the Ormel et al. Pebble accretion stuff, right?
Do they? A lot of people will insert a planetary core.
Right. So what they actually do is they start with planetesimals. Right. I think they start with planetesimals, see the growth up to embryos, and up and over again. So the beginning, I think the most sophisticated ones start with things which are 100 kilometers in size, 10 to 100 kilometers.
Okay. Any other questions for Subbu? Did that answer your question, Oliver? I mean, that was just the thermal structure of the disk, but
Yeah, that clarifies it definitely. And basically, the rest would be just the follow-up discussions on that. But he basically said that. So very cool.
yes, Timmy, please.
So I was wondering, like, since you guys solved like for the 1D gas evolution equation, did you? So you know now, I mean, I guess you know, but you have like this Tabon et al. 2022 model where they kind of like revisited. I mean, I'm not especially a big fan of this model, but like it's like an easy model to, instead of only having the viscosity, you also have like the winds, like in the form of like this 1D equation. So that would be very interesting because like, although I'm not convinced, I mean, for me, it's like a lot of debate whether or not winds can be super effective very far from the star. But like, I would say like it's very likely that the winds will drive mostly the angular momentum in the inner regions. So then what if like you try to kind of like solve for this equation, and then you can play with you have your alpha for the MRI, but you can just put the parameters alpha for the wind, kind of. And then like, what would you expect to see?
Yeah, I know. I don't think, I mean, I think physically, I don't think that's very feasible. And so it makes, or I guess say a little bit about the underlying physics here, right? So when you have the MRI operating, there is a magnetorotational instability. The alpha is really coming from the turbulence, right? It is a turbulent gas, right? But when these people invoke the outflowing stuff, so MHD outflows and winds, then this is really coming out of the Hall shear instability, right? So this is essentially Schoening-Bai's stuff, right? So, but the Hall shear instability really comes in when the magnetic field becomes so strong that it shuts off the MRI.
Okay. Maybe it does.
I mean, maybe it does, right?
This is my point. My point is like,
Yeah.
because like here we assume that the MRI drives there.
Well, exactly. So I've had conversations with Schoening about this, right? And really and so if you look at his simulations only go into around 0.6 AU, not inwards of that, right? And so we are actually inwards of that. Okay, and if you talk to Schoening, he will tell you that in these really hot regions where the alkali is, ionized thermally, etc., their eye, as in Schoening, would be also surprised if the MRI is not active.
Yeah,
okay.
I guess my question is not that the MRI,
So,
for sure the MRI is active.
Yeah, but to include the MRI and winds at the same time, one could do that figuratively or in a parametrized fashion, but I'm not even sure that would be the right physics at all, because it's not clear to me that the two things can happen at the same time.
Actually, I think they do. Like, I know if you look at like, I can never remember her name, but Khan is her last name. Khan Sui.
Okay.
She was at Cambridge, and she also worked a lot with Schoening.
Okay.
And she actually like worked on this, like to see like if it's compatible to have MRI and winds together.
Okay.
Showed that it's like compatible. You can actually have both MRI and winds together.
Okay, so it's just a layer thing, is it?
Sorry?
It's just a layer thing, upper layers, lower layers, that sort of stuff.
Yeah, so like there will be more like the MRI can locally kind of drive some turbulence and therefore angular momentum, but then the bulk of the angular momentum transport will be like driven by the winds like in the
okay, I'll have to look
like,
that up.
High layers.
Okay.
Because I think the mechanism are not like they are not like antagonists. Like you can have both together. Because MRI just need ionization, winds just need like a magnetic field and kind of braking and the right kind of angle.
So if that is the case, I mean, okay, I will freely admit that if you turn off the turbulence, right, then it'll solve a lot of things. Okay, we'll have a lot more coagulation. Pebble accretion is a lot more efficient if your turbulence is lower.
But also your trapping efficiency at the dead zone in a boundary.
Right. So
yeah, but you may not have.
Well, you may not have it. Well, I've got to have some boundary. So I've got a dead zone. I do want something to happen. But I was going to follow up on this point here. the efficiency of trapping could be strongly affected by as you mentioned, it's the turbulence that is inhibiting the trapping. So if we do something to change this turbulent profile, Timmy is suggesting with also the winds, then
Yeah.
we could.
But again, I think my question is more fundamental than this. You may not actually have the dead zone. So like the dead zone is like a ionization thing, but like basically like here when people like talk about dead zone, they always do the same. So like you have a dead zone for ionization and dead zone for turbulence. And since like the MRI is kind of like both because MRI is from the ionization, and then you have a dead zone, the dead zone MRI is the same as like the dead zone turbulence. But now if you have winds, you may have a dead zone for ionization in the sense that you have a big increase in ionization. But since the winds are not super like sensitive to the microphysics, then for the turbulence, and I mean the angular momentum in general, then like it will not matter for the alpha if you compute an alpha. So you may have like a jump in ionization, but since like now the angular momentum will be transported by the wind, you may have like a constant alpha, for instance, for whatever reason.
Well, remind me, because this brings the whole effect works one way if the global field is one way, and the other if it's the other. I mean, for half the systems, we do want to stop this happening, right? So we do want to kill the dead zone or kill the boundary.
Yeah, but I think like the thing is like no one really understands. I mean, the whole effect is like a beast on itself. Like there's like a lot of things like the whole effect and is like a beast compared to like chromic and American diffusion. Like a lot of things are not known.
And really, I mean, I do remember at that time I was excited about this idea. Maybe half the systems have this and half the system don't. But I'm more and more of the opinion now that really the thing that matters is if you have a giant planet out there, right? So it's really the supply to the inner disk that is being controlled by a giant planet.
But if planets are leaky, I mean,
yeah, but how much do they leak in dust? In solids, right?
Well, I think it's quite leaky. Stuff can still get past.
But again, I think we don't have the simulation for this.
We don't, and in fact, at the moment, James Owen and Richard Booth are applying to do exactly that, right? Because we see that there is also a strong correlation between some correlation between the metallicity enhancement or not of the central star, and if you have a giant planet around, right? So the idea being that
why would half the systems have a giant planet and half are not?
So that's another one about the giant planet formation, right? And in 1 year's time, you're going to get an inundation of information from Gaia, right? Which you'll finally be able to get these cool Jupiters. So we'll know that. But
very good. In Virginia, are there any questions there? I want to make sure we don't leave you there. Or any other questions online? Maybe I can do one last. So I like forming things like this dead zone in a boundary, and I know you've said the pressure maximum is quite weak, and
I don't know if that's true or not until I do the actual calculations.
But in the inner disk, it just seems to raise more problems.
Well, so here's the thing. Okay, so I want to show another plot here, right? You might want to trap things, but here's an issue, right? So in our calculations, this is where, so the upper plot shows issues about the streaming instability, right? So the idea in this inside-out planet formation is that you trap a lot of stuff in the pressure bump, and then eventually when the gas ratio is high enough, you have the streaming instability kick in, which can concentrate things even more. And finally, all that solid material concentrated undergoes a gravitational instability to collapse, okay, into planetesimals, 100-kilometer size objects, and then onwards and upwards, right? But first of all, you have to satisfy the constraints for the streaming instability, right? So again, this is in light of our simulation, so I don't know how much it's true, but at least for our case, in the top panel, you can see the two streaming instability conditions are in the dotted line here and in this other line here, right? And our simulation results, dust to gas ratio, is a solid line. And you can see that we are above, in other words, we satisfy the streaming instability conditions only in this very narrow region close to the pressure pump. Okay, so it may be that our answers here are not exactly right. Maybe that'll improve. I don't know. The other problem, which I think is much more severe, is if you look at the lower plot, you have this Roche limit plot here. This is the solid line. Okay. And this Roche limit thing is where basically the gravitational force of the central star is able to overcome the local gravitational forces, if I were to put that simply, and therefore prevent gravitational collapse. Okay. And here, and that Roche limit has got nothing to do with anything else, just got to do with the central star. And it falls off as R to the 3, right? Or so something of that sort.
I think so.
Right. So in other words, it falls off as R to the 3, and therefore also it rises very steeply inwards, right? And so if we just overplot on that, over densities of 100 times that of the gas, 1,000 times that of the gas, 1,000 times that of the gas is the kind of thing that the streaming instability gives you. Okay. Even if you do that, you can see that even at 1,000 times, there's a very small area close to the pressure maximum where you're above the Roche limit. If you go inwards, then in fact the Roche limit eats you up. You're not going to be able to collapse things. Okay, so this is why I increasingly feel like in order to construct planets in here, you need to have something which is already a solid, as big as an embryo.
Depends on your trapping efficiency. If your trapping efficiency is high, you'll concentrate a lot.
More than 1,000. You'll have to go up to 10,000 or 100,000. Right? How high do you want to
Okay,
get?
at some point it's unrealistic to think.
Well, but it's
very hard to
you're.
calculate.
I don't think we're using gravity to make the planets. So
Yeah, but when you
Of
have
course you are, you have
a collapse and there's sedimentary.
Yeah, you want.
So the streaming instability is more like you concentrate them, but then eventually they actually like the end of process is like
Is it
gravitational
gravitational
collapse.
instability?
So like if they don't collapse on themselves, then you can't probably find someone.
Right.
But yeah, I just would like to comment this because like I think the streaming instability, like even though it's like something that is super like trendy right now, like it's still very unknown because like they still have like even the streaming instability like community, you have debate whether or not the streaming instability can happen at the pressure maximum. So the nice thing about pressure maximum is that you want all the particles will be trapped there exactly at this location by definition. But the issue, some people think that the streaming instability doesn't occur at this exact location.
something will happen. They will just keep accumulating and.
Yeah, sure. But the thing is, like now, like as for like in the case of like Maya's work, you can see like the peak in dust to gas ratio is very sharp. It's not like it's not like something like super shallow. It's like very sharp and just like very well defined. So you just only have a tiny like region where actually like you have very high dust to gas ratio, and then it falls off like very,
Also
like,
very
quickly, beyond or like within this location. So actually you only have maybe one small location, a few like tens of AU where you actually have the right conditions. But now if the streaming instability doesn't occur at the pressure max, then actually like it becomes more and more stringent. And I feel like in Maria's work in this paper, there's like, so she used like kind of like those kind of like criteria that people usually use. But now if you again like talk to like streaming instability people, they will tell you that you need to have very high Stokes number. It's actually very hard to have very high Stokes number. Some people like if you like talk to Shao Xingyang, for instance, he will tell you like that you need a Stokes number of equal 1 for the streaming instability to occur. It's almost impossible to have Stokes number equal 1 in most of like the normal disk conditions.
Will depend on the size of the particle.
Well,
It depends
yes.
on the size particle, but then the thing is like if now you have like a very stringent fragmentation, and like it depends on everything, but like if you do the calculations, then you never have like a Stokes number equal to 1. Because again, like if you are close to 1, then they drift also very fast. So that's the other issue. The closer to 1 they are, the faster they can drift in, and then the more you lose them.
What would they? Well, but not in a strong pressure trap. We're at the hour. We can continue the discussion further into the night, but let's stop the recording first. So thank you.
Thank you, everyone.